Okay, in the previous we have seen about formation of p-n junction diode or how to form a diode. Now we see how a diode works or biasing of a diode. Biasing is the application of DC voltage to a diode to make either conduct or block a current. So when a diode is connected to a battery as shown in the figure below, holes in the inside are forced to the left. That means opposite charges attract each other. That the negative terminal of the battery attract the holes of B side. And also electrons in the P side are forced to the right side. So the result in an empty zone around the p-n junction that is free of charge carrier, creating depletion region. That is high resistance creating in this p-n junction. So this depletion region acts as an insulator, preventing current from flowing through the diode. This arrangement we can call it reverse biased. When I show you the circuit, the diode anode terminal and cathode terminal. When the anode terminal connected to the negative terminal of the battery and the cathode terminal of the diode connected to the positive terminal of the battery. During this arrangement, the negative terminal of a battery attracts the holes of P side. That means the holes move to the left side. While when the positive terminal of the battery connect with the cathode side of a diode, the electrons also move to the right side. So this arrangement we can call it reverse bias. That means current cannot be moved freely. So the diode, it looks like open circuit that prevent current move from N side to the B side. So this arrangement reverse biasing. In another arrangement of diode, that means when a diode is connected to a battery as shown in the figure below, electrons from the N side and holes from the P side are forced toward the center by the electrical field supplied by the battery. The electrons and holes combine, causing the current to pass through the diode. This arrangement we can call it forward biased. So when a diode connected in a circuit, anode part of a diode connected to the positive terminal of battery, cathode side of the diode connected to the negative side of a battery. So this arrangement we can call it forward biased. During this connection, what was the result? What's happened? The positive terminal of a battery directly connect with the holes in the P side. That means the same charges repel each other. So the holes forced forwarded while the electrons in inside also connected with the negative side of the battery. Again, the same charges forced forward. During this time, The holes and electrons combine that causing current can be flow from positive to the negative side. That means current can be flow from P side to N side. So at this condition, a diode will conduct it. So this method of connection or arrangement, we can call it forward biased. Diode characteristics, voltage versus current characteristics of a diode. A practical circuit arrangement for a p-n junction diode is as shown in the following figure. An ammeter is connected in series and voltmeter in parallel, while the supply is controlled through a variable resistor. Or we can use variable battery source, we can use it. During the operation, when the diode is in the forward biased condition at some particular voltage, the potential parallel gate is eliminated, such as a voltage is called as cut-off voltage or knee voltage. If the forward voltage exceeds beyond the limit, the forward current raises up exponentially, and if this done further, the device is damaged due to overheating. Yeah, don't exit from the limiting of forward voltage. So when a diode connected in a circuit with a battery, negative, positive battery, this battery is like a variable DC source. The positive connect with the anode side of a diode. The cathode connect also with ammeter, and the output of the ammeter connected to the negative side of a battery. And then also connect a voltmeter in parallel with a diode. So during this result, what's happened in this diode? So when you graph like Y connection as a current, the x-axis as a voltage represented, during forward, when our source is exceeded or greater than 0.7 voltage, let's assume this diode is made or formed from silicon. The diode, it becomes starting of conduct. So when you increase the source of a battery, the current, it becomes rising exponentially. So during this forward condition, when our source is exceeded beyond that limited forward voltage, the diode become damaged. So according their forward voltage must not exceed the limiter of forward voltage. So this is the output character of forward condition. So the current becomes exponentially increase, and the voltage approximately 0.7 at that diode, that is silicon. When you have a germanium, the nil voltage or cut voltage, it becomes 0.3. So in our lecturer, most example we use silicon type of diode. So now, as you see in the figure, forward biased diode and current versus voltage characters during forward bias. When the diode is connected with the variable DC source, that means positive terminal of the battery with the anode side of a diode negative terminal of a battery with the cathode side of a diode. During this time, when you increase forward voltage, the current becomes increased. So that means exponentially increased. So the following graph shows the state of diode conduction in forward and reverse biased condition. So during reverse bias, current produced through minority carriers exists known as reverse current. As the reverse voltage increases, this reverse current increases and it suddenly breaks down at a point, resulting in the permanent destruction of the junction. So, what does mean? The negative terminal of a battery connected with the anode side and the positive terminal of the battery connected with the cathode side. During this time, when the reverse voltage increases by the means of minority carrier, we can get few currents. But when increase the reverse voltage, also reverse current becomes increased. But suddenly destruction to the diode. That means the diode permanently damaged. So the current become increasing. So by the means of beyond or exceeded of reverse breaking voltage. That is, this become we can call it by means of reverse breaking voltage. During these conditions, the diode is out of source or permanently damaged because during the reverse it becomes conducted. Now, during reverse bias condition, we can get maximum reverse voltage. That means peak inverse voltage. Peak inverse voltage is shortly called as PIV. It states the maximum voltage applied in reverse bias. The peak inverse voltage can be defined as the maximum reverse voltage that a diode can withstand without being destroyed. Hence, this voltage is considered during reverse biased condition. It denotes how a diode can be safely operated in a reverse bias. As shown in the figure, the circuit is reverse bias arrangement. That means the diode becomes an open circuit because the current cannot be flow through the diode. So during this condition, when we measure as that diode, we can get maximum voltage that we can call it peak inverse voltage. So this peak inverse voltage always equal to with the input voltage. That means the maximum input voltage without being destroyed the diode. So this measurement we can call it PIV or peak inverse voltage. Diode resistance. Diode resistance can be defined as the effective opposition offered by the diode to the flow of current through it. Ideally speaking, a diode is expected to offer zero resistance when forward biased and infinite resistance when reverse biased. However, no device can ever be ideal. Thus, practically speaking, every diode is seen to offer a small resistance when forward biased and considerable resistance when reverse biased. So when you see forward resistance, even after forward biasing, the diode will not conduct until it reaches a minimum threshold voltage level. After the applied voltage exceeds this threshold level, the diode starts to conduct. The forward resistance is nothing but the resistance offered by the diode when diode is working in its forward biased condition. So forward resistance is classified into two types, static or dynamic, depending on whether the current flowing through the device is DC, direct current, or AC, alternate current, respectively. So as shown in the graph, diode resistance shown as part of diode characters. Let's see the types of forward resistance. 1. Static or DC resistance. It is the resistance offered by the diode to the flow of DC through it. When we apply DC voltage to it, it's shown by the black dotted line in the above figure. So mathematically expressed static or DC resistance RD, resistance of diode during DC resistance, is equal to VDC over IDC. This is expressed for static type of forward resistance. For the second type of forward resistance, dynamic or AC resistance, it is a resistance offered by the diode to the flow of AC through it when we connect it in the circuit which has an AC voltage source as an active circuit element. This is shown by the slope indicating red solid line in the upper figure and is expressed as like static. We can express it mathematically for dynamic or AC resistance. So RAC is equal to voltage AC over current AC. This expression mathematically for dynamic or AC resistance. So during reverse resistance, when we connect the diode in reverse biased condition, there will be a small current flowing through it, which is called reverse leakage current. Even in the reverse state, one can experience the flow of minority current through the device. Due to this current flow, the diode exhibits reverse resistance characteristics, which is shown by the purple dotted line in the above figure. The mathematical expression for the same is similar to that for the forward resistance and is given by reverse resistance equal to voltage reverse over current reverse. So by this expression we can define reverse resistance in mathematically. Diode specification. So as lists below provide detail of various diode characteristics and diode parameters found in the datasheet and specification for diodes. When you need to buy a diode from the market, you must know where they apply. So according to their application must be selected according to their datasheet or specification of the diode. So must be C, semiconductor materials, diode type, forward voltage drop, what is the maximum forward voltage of the drop according to their application, peak inverse voltage during reverse time before destroying the diode must know peak inverse voltage according to their application where to apply. Maximum forward current must know junction operating temperature, that's the depletion region operating temperature, leakage current, junction capacitance. So these parameters must know. Let's say example. There are many different diodes with a large number of different specifications. It sometimes helps to see what the various specification parameters are and how they are expressed in a similar format to this in the data sheets. As seen, example, typically 1N5711 characters or specification are shown in the table. So by this method, you can identify what type of as you want to do your application of your circuit. Diode equivalent circuits. An equivalent circuit is a combination of elements like resistor, inductor, capacitor, etc. properly chosen to best represent the actual characteristic of device in a particular operating region. So We have three types of diode equivalent circuits: piecewise linear equivalent circuits, constant voltage drop or simplified equivalent circuits, and ideal equivalent circuits. So this circuit is here. It is a piecewise equivalent circuits. The second one, simplified equivalent circuit or constant voltage drop equivalent circuits. The third one, ideal equivalent circuits. So why use that equivalent circuits? Because you cannot use traditional circuit analysis like Thevenin theorem, Norton theorem, superposition theorem with actual devices. If you have a diode or a transistor in your circuit, you want to analyze traditionally Norton theorem etc. to find out the parameters like voltage or current. With this actual device, impossible. So must be defined thus simplified equivalent circuits like piecewise simplified or ideal. So replace the simple equivalent circuits. Then we can also use traditional circuit analysis. So piecewise linear equivalents, we have a voltage parallel or potential parallel, and also we have dynamic resistor, and this ideal diode represents the direction of current. So in the graph, it's similar to the characteristics of a diode. So two straight lines that join it. So this one is a threshold voltage or barrier potential, and at this point we can get dynamic resistance. So dynamic resistance is equal to 1 over slope. Slope is equal to tan theta. Tan theta, that means 0 perpendicular over the base. So this perpendicular represents the ID and the x-axis represents the VD. So RD is equal to VD over ID because R is equal to 1 over slope. So and also in second that equivalent simplified equivalent circuit or constant voltage drop equivalent circuit is the most model used in circuit analysis. So during this circuits only we have parallel potential or voltage parallel, and the direction of currents represents the ideal diode. So during the graph represents its straight line. That means R is equal to 0. So tan theta is equal to the slope is equal to infinitive, or tan theta infinitive means or tan the theta when you find tan inverse of theta, that is during infinitive at 90 degrees. So this represents parallel potential. So during simplified equivalent circuit or constant voltage drop equivalent circuits, RD is equal to 0. This last one, ideal equivalent circuit, is only the direction of the current represented, that is the symbol of the diode. During this characteristics, when you represent in the graph, perfect, when VD is greater than 0, perfect conductor. When in the reverse, VD is less than 0, perfect insulator. This is for ideal equivalent circuit represented. So this is about diode equivalent circuits. In the next, we will see about diode analysis.